Okay, so that's the first part, but I'll assume that most of you have at least heard part of this, so it'll be pretty quick, and I'll highlight the main important points. And then I'll be talking about how this kind of splits emerge from a very simple property about these u variables that this curve integral is defined with, about a feature about like surfaces that are within subsurfaces that are within surfaces. Anyway, we'll get back to it in a second. And then at the last part, very quickly, I'll explain how we can use them to access soft limits, which now can be for a more slightly auditive is this pions and gluons, precisely because recently we've seen that we can connect pions and gluons to scalars in a simple way, which I'll also describe. Okay, so let's start. So this curve integral formalism describes amplitudes in this very simple theory of colored scalars that goes by the name of trace phi cube theory. So just practically, the amplitudes are extremely simple. This is scalar theory, so they're only functions of the dot product of the momentum of the particles in the scattering process. And the singularities happen precisely when sums of consecutive momentum go on shells. So their momentum squared goes to 0. So a nice way of sort of encoding the information of what are these kinematic invariants that correspond to singularities is by drawing the momentum of the particles that enter in the scattering process tip to toe. And because of momentum conservation, they form this closed polygon. And so if we consider the length squares of distances length squares of chords in this polygon, which is what I'm going to call these xij's, these precisely corresponds to the variables that appear as singularities. They're given by sums of adjacent momentum, which in other words correspond to precisely the propagators that appear in the planar diagrams. So then we can summarize that like at tree-level amplitudes in this theory can just be given by considering summing over all the triangulations of n-gons. And for each triangulation, we get a factor that is 1 over the product of the chords appearing in the triangulation. So here I have an example at 5 points. There are 5 different ways of triangulating the pentagon. Each of them gives me precisely one of the possible different 5 planar diagrams, and I get these sort of 5 different factors. Exactly the same story goes through at loop level. The only difference is that now instead of having a polygon, I have a punctured polygon, which I'm just going to replace by a disk. And so if I can consider all the possible ways of triangulating the punctured disk, then I get exactly all the possible Feynman diagrams. And once more, the curves entering the triangulation are precisely the kinematic variables associated with the propagators entering the diagram. So here you see at 2 points, I have 2 tadpole-like triangulations and a standard bubble. Okay. So the curve integral formalism tells us that the sort of amplitudes in this theory, or more precisely, they're sort of string amplitudes that at low energies gives us these trace phi cube theory. Well, I don't actually have to write them down. Thomas Lamb wrote them in the morning. So it's exactly this integral that you have here. The first part is this canonical form that we have here. So it's written in terms of these positive parameterization in terms of the y variables, which I'll describe in a second. And then we have this extra factor, the regularization, the Kober-Nielsen factor, where it's a product of these u variables. Each u is associated with a curve that you can draw on your surface. And then the exponent of these u's are precisely these kinematical variables. Okay, so this is what's called the Kober-Nielsen factor. It also has okay, so at tree level, this is extremely simple. There are a finite number of curves on the surface. I have a finite number of u's, and I take the product of all those u's. And I'll give an explicit formula for that in a second. But at loop level, things get more interesting. I would just like to highlight that. From the moment that my surface has a puncture, then there's now an infinite number of curves that I can draw on the surface. That comes from the fact that they can self-intersect an arbitrary number of times around the puncture. Okay, but so just to be concrete, this is basically all that I'm going to say about this formalism. So here, this measure, this d-log form that we have on the y's, we should really think of it as being kind of associated to a choice of a triangulation of the surface that we're considering. So here I have the disk. This is the tree level 5-point case. And I pick this triangulation, which is naturally associated with what we call a fat graph, just a diagram where the propagators that I chose are precisely the chords entering in the triangulation. And so in that case, my measure is a function of these 2 y's that I picked. And then I can write this I have 5 different curves that give me these 5 product over these 5 different u's. And now these u's depends on the y's on a certain way, which you explained at the beginning of the month, but this has a very nice interpretation as a problem about the curve that you draw on the surface. It comes from a counting problem. Anyway, and these are some f polynomials on the y's. But when you replace it, you get some integral like this. So it's just, some simple polynomials in the y's, and the exponents are precisely the momentum that the amplitude depends on. Okay, this is what the amplitudes look like. But I would say the most important, the reason why we like these U variables is because they make manifest this most basic property of amplitudes, the factorization near poles. And this comes as a very nice consequence of these U equations that these variables satisfy, which here I have. So I'm so sorry, this big button. Okay, so if we have the U variables associated to a given curve C on the surface, and we take the product over all the remaining curves on the surface that I'm calling C prime, where the exponent is the number of times that C intersects C prime, then this has to be equal to 1. So you see there are as many equations as there are U variables, but still at tree level already, there's an n-3 dimensional space of solution because we parameterize the U's in terms of the Y's that solve these equations. In addition, this equation tells us that if we look at the domain in which the U's are positive, then automatically all of them have to lie between 0 and 1, precisely because, I mean, these are positive quantities that add up to 1, so all of them live between 0 and 1. And these integrals, like the sort of amplitudes, when a given x, so the exponent of a given U goes to 0, then the integral develops a singularity precisely when this corresponding U goes to 0. And so from the U equations, so if a given Uij goes to 0, then all the ones that cross it, so that appear in this product with a non-zero exponent, then automatically have to go to 1, so that these equations satisfy. This is what are called the binary property of the U variables. And so we see that in the Kolbe-Nielsen factor that we had on our amplitude, that have the product of all the U's, when we go near this locus where a given U goes to 0, then the contribution from the curves that cross all go to 1, so that this factor precisely factorizes into the product of those living on the left and the product of those living on the right. And so we're producing precisely the factorization that we expect on this locus. So this is why U variables are just nice to describe these amplitudes to begin with, but what I'm going to be telling you about is that they also make manifest this other type of factorizations. So these factorizations that we just talked about is that we pick a given curve on the surface, right? And like we sort of go on that pole so that we cut the surface into two. We take a residue and we land on this. At the level of the sort of fat graph that is describing the surface, it's the same thing. I just cut the sort of big surface on an internal edge and I have the product of two. But crucially, I mean, I need to cut. So if I glue these two surfaces together, right, I'm producing a new internal edge by gluing them together. And that's why precisely I need to sort of go on the residue. So these sort of split factorizations are slightly different. The question that we want to ask is there any way in which I can join surfaces together without producing any new internal edges? So that I basically don't have to go on a residue to land on this factorization. Here I have to go on a residue because when I glue the surfaces together, I produce a new edge. So I need to take a residue to land on this factorization. And the answer is yes, this can be done by simply overlapping the two surfaces on a triangle or on a vertex. So here's a simple example of how this is done. This is going to be more concrete now. So you see I have two like little surfaces, S1 and S2, and I join them in a way that like they overlap precisely in a vertex. And you see, in this way of overlapping them, all the sort of internal roads of the full surface that you get by joining these two surfaces, the sort of internal edges, are either an edge in S1 or an edge in S2. I didn't create any new internal edge that was not already there in S1 or S2. Anyway, so in other words, and from the sort of surface perspective, what I'm doing is I have two subsurfaces that precisely overlap on a triangle. And as we'll see in a second, I can build kinematics so that my amplitude factorizes into these two lower subsurfaces that does not require going on a pole. So for a more specific case of these situations, when J is equal to I plus 1, and this particular split pattern is what's going to be relevant in a second to derive multi-soft limits, as you'll see. Okay, so let's see how we do this. We want to find kinematics in which the amplitude factorizes into the amplitudes of the two lower surfaces. So the first thing to note is precisely by this requirement that my two surfaces overlap on a triangle, right? So like the sort of measure, which is the dy over y, which each y is associated to an internal edge, naturally factorizes into the measures of each subsurface, precisely because each internal edge either belongs to S1 or to S2. That's sort of the thing that I required. So maybe, anyway, so this is the measure automatically factorized. What I want to know is if there's any limit, any kinematics that I can put there that these Kobe-Nielsen factor also factorizes into the lower point surfaces, so that in the end, I get something which can be sort of the product over the u variables of the smaller surface S1 with its respective kinematics, and a similar thing for the subsurface S2. So this is the question that I want to ask. And it turns out that this is extremely simple, and it comes out just as a consequence of basic properties of the u variables. A natural question that one can ask is whether I can write the u variables of one of the subsurfaces in terms of the u variables of the big surface. So here I say the u for a certain curve C1 in S1 that satisfies its respective u equations. Can I write it in terms of the uc of the big surface? And the answer is extremely simple. Turns out that all that I have to do is consider all the possible ways in which I can extend a certain curve C1 in the smaller surface into curves on the big surface. Okay, so more in particular, so here I say that the u C1 in the subsurface, I take the product over all the curves on the big surface, where the exponent is basically the number of times that the little curve C1 is contained inside this big curve C. So here I have an example. If my subsurface is this shaded pink region, one possible curve is this C1, and the two ways of extending into the big surface would be these continuations in blue. So here the u of C1 would be just the product of these two u's of the curves in the big surface. Okay, so and so using this, I can just kind of automatically build the kinematical locus in which this factorization will happen. If I start with this product of the two lower point amplitudes, and then I plug in their u variables in terms of the u's of the big surface using this extension formula, then automatically I have an integral which is now over S, over the full surface, and the exponents of each u associated to curves on S now can just be written off as linear combination of the kinematics of the curves on the smaller surface, and that tells me precisely what is the kinematical limit in the big surface that lands me on this factorized problem. Okay, so this is what it comes out to look like, but this actually satisfies a very nice graphical rule. This split kinematics, which is what we call satisfies an extremely simple graphical rule, which is the following. So if I draw a given curve X on the big surface, then in the split kinematics, it becomes the sum of the curves that it decomposes into in the smaller surfaces. So here you see this black curve X, inside S1 becomes this little curve X little H1, and inside S2, this blue curve X2. So under the split kinematics, we just have to evaluate the full amplitude in X's, in this case, equal to little x1 plus little x2. Okay, but so the first thing that we can note is that the sort of number of kinematics in S1 plus the number of kinematics invariants in S2 is smaller than the number of kinematics in the big surface. So this is just telling us that going on this particular kinematical locus, we are imposing some linear constraints between the x's. So this is a restricted kinematic, this should not be surprising, under which the amplitude factorizes. And so I'll now try to explain what this kinematical locus looks like with an example. So let's look at a very simple case at 6 points, where I consider my first subsurface to be S1, or it's 2, 3, 4, 5, and 6. So I have here in green, and S2 is a 4 point with 1, 2, 5, and 6. And I'm going to denote the kinematics of S1 with X and S2 with Y. So following the graphical rule that I just illustrated, the curve X13 decomposes into a boundary in the region 2, which is just a curve between two adjacent edges. But in like subsurface 1, it actually is not a boundary curve, is what we're going to call X36. I mean, is the curve X36 in S1. Similarly, for 1,4, something completely analogous happens. It's still a boundary curve inside S2, but it's a non-boundary curve inside S1, which is just X46. Anyway, so if we keep doing this, we have the same X15 lives strictly inside. Anyway, that's a bit boring, but the more interesting curves are these ones. For example, now X36 crosses both surfaces. So that means that it's going to map to the sum of two different kinematics. So inside S1 is again curve X36. Inside S2 is now curve X26. So we get this sum. And similarly for curve X46. Anyway, so the claim is that if I start with my 6-point amplitude in this trace phi cube theory, which has 14 different terms in the sort of x's, the curves of the original surface, and I plug in this kinematic mapping that I highlighted here, then it will factorize into precisely the 4-point amplitude of S2, this little part, and the S1, okay? And I mean, you can check it, but it's just this is what happens because of what I derived. And so this is what happens. But still, I mean, like phrased in this way, the particular sort of kinematical locus or restriction that we're imposing is not super clear. So to actually understand what these linear relations between the x's that we're imposing are like, what we can do is start by identifying a specific subset of our like x's on the big surface that map to single curves in the subsurfaces. So these are the ones here I highlight in red. And then all the remaining ones that are not these special guys are just always going to be linear combinations of these red guys that I highlighted, because every curve on the big surface is always going to decompose into curves on the smaller surfaces, just by construction. So anyways, so I can write these equations as linear relations between the big x's that ultimately I can just simply phrase as dot products of two simple momentum being set to 0. Okay, so here is the point where we can make contact with things that had already been seen in the literature for tree-level amplitudes, first pointed out by Freddie and Nick, with using CHY, this so-called split kinematics, where again you set these sort of non-planar, you see 2 and 6 are non-adjacent indices, and the same for 3 and 6. So these are, you set non-planar dot products of momentum to 0, and the amplitude factorizes. A sort of further case of this, where you keep factoring into lower points and lower points, is what gives rise to minimal kinematics, which Nick will also talk about later this week. Anyway, but the sort of key point that I want to emphasize, from the moment that we understand this from the surface perspective, now all these statements just generalize to all orders, right? Because now I can really start with a surface that is arbitrarily complicated, so beyond the tree level statements that have been identified. So here I have an extremely complicated example. It's like, I mean, not extremely, but complicated. I have three punctures, and I identify S1 and S2 that still overlap on a triangle. And now I can just read off what is the split kinematics mapping exactly the same way. I draw a curve on the big surface, and it maps to precisely the sum of the curves that it decomposes into in a smaller surface. And in this limit, the amplitude should factorize into the product of the two lower surfaces. So here in this case, it will be the sort of integrand that we get. Okay, so now, yes, I'm going to move on to describe how we can use splits to access soft limits. So soft limits are limits where one of the momentum of a given particle is taken to 0. For a trace by cube theory, they're not that interesting, but people care about them for gluons and pions, which I'll get to in a second. But they're basically a kinematical mapping in terms of the x's, which I'll explain. So here I have the summary of what we saw at 6 points. And what I would like to point out is that we've further considered a limit where all the kinematic invariants inside S2, in this case the y's, go to 0. Then this map reduces to something even simpler. We see that both x15 and x26 go to 0. And on top of that, x46 and x36 become just equal to the x's, and so now become equal to respectively x14 and x13. So here's what it becomes to. And you see, this is precisely the mapping that I would get if I consider the limit in which points 1 and 6 collide on the same point. In this limit, curves 1, 5 and 2, 6 become boundary curves. And on top of that, I mean, every sort of curve 4, 6 that ends in 6 becomes the same thing as the curve that ends in 1. So, and the limit where punctures 1 and 6 collide is precisely the limit where I have that the momentum associated to particle 6 goes to 0. If you recall the sort of momentum polygon picture that I drew in the beginning, each boundary is associated to the momentum of the sort of adjacent particle. Okay, so this is the sense. So here we saw how we can access sort of a single soft limit in this example that I just showed, where we send, like we have a 4-point here, and if we send the y's inside this 4-point to 0, then the split limit is precisely the sort of single soft limit where P6 goes to 0. But more generally, if I consider a split pattern where I have a certain S1, and here I have an S2, where I have m particles plus 3 in the bottom, I believe, then in the limit where the sort of invariants of these S2 are taken to 0, then I precisely get, like, the mapping turns into precisely the limit in which I am sending m particles soft. So I'm basically colliding all these indices together. Okay, so from split kinematics, we can, from these S2 factors, precisely going to give rise to what we usually call the soft factor, and the remaining part is the lower point amplitude that we expect to have. Okay, so to end, I'm just going to quickly review, like just in words. So recently, we've seen that from the surface integral formalism, the curve integral formalism, we can really connect quite different theories. So we can access pions and gluons from trace phi cubed amplitudes by a very simple kinematic deformation. So I just started with the amplitude, the surface integral for trace phi cubed amplitudes, and I shift the kinematic invariance xij plus this delta ij, where delta ij is plus delta if both I and j are even, minus delta if they're odd, 0 otherwise. This is going to sound very crazy, but I mean, if you sat on one of these talks, you probably have some idea why this is the case. But the sort of but you just have to believe me that at low energies, then for different values of delta, for delta equals to a non-integer value, we get the NLSM. For delta equals 1, we get gluons at low energies. But all that it matters is that for these purposes that they can be reached by a simple kinematic shift of trace phi cubed. And the more non-trivial part is that this delta shift is so special that it precisely like commutes with split kinematics. What I mean is that it's compatible with the sort of kinematical restriction that is imposed by going on kind of the split kinematics. Okay, so, and what this means is just that all the splits that we find for trace phi cube theory are also there for pions and gluons. Okay, and so crucially, then we can also use them to access multi-soft limits when we send the kinematic invariance of one of the subsurfaces to 0 at all orders. Okay, so I'm just going to summarize what we get for pions. For gluons, we're still exploring it together with Jeff, who's here. But for pions, things are actually extremely simple. So at all orders, using the splits, we can show that any odd soft limit, so if we send an odd number of particles to 0, then that the integrand vanishes regardless of how many loops we're in. So this kind of generalizes the Adler zero. So for pion amplitudes, it's famously known that if we send a single pion soft, the amplitude should vanish. Turns out that this result is general for an odd number of adjacent pions going soft. While when we send an even number of pions soft, things a little bit more interesting happen. So we first land on a split where we have a tree-level process on S2 and a loop-level process on S1. And then when we further take these Yij's to 0, we land on this soft prefactor of 2m pions going soft, but then we actually can have an explicit formula for this because we have an interpretation of the soft prefactor as a sort of delta-shifted trace phi cube amplitude that precisely matches a mixed amplitude of pions and scalars. Anyway, what important is that there's an explicit formula for any number of pions going soft. Okay, so this is all that I want to tell you about today. I started by just briefly reviewing how we can phrase these amplitudes of trace phi cube theory from this curve integral perspective that not only makes manifest standard features about factorizations of amplitudes near poles, but also just completely conceptualizes this new behavior that is now away from poles. Just by simply identifying subsurfaces that overlap on triangles or vertices, we can just, by knowing the extension formula of the U variables of the small surfaces into the big one, we can automatically build the kinematics that makes the amplitude factorize not only at tree level, but now at all orders. And in particular, if we sort of consider the further limit where the kinematics of one of these factors goes to 0, then we can access this interesting physical limit of multi-soft limits for both trace phi cubed and pions and gluons. And that's all. Thank you.